Today I'd like to go over the practice problems for the first lecture exam. These practice problems are designed to test your knowledge of the concepts. So if you can get these, you're in pretty good shape. If you're having trouble with them, you may need to go back and study that particular chapter. Now the thing I want to stress though is these questions are not going to be exactly what the test questions are going to look like. They're going to look different because we can't just show you how to solve all the problems. There's about 10 different ways we could ask any one particular problem, and this is just one of them. So if you understand the concepts behind these problems and you have no trouble answering them, you'll be in pretty good shape for the exam. So the first problem is just simple nomenclature items. This section is just a lot of memorization. So the way that I approach nomenclature for the ions, so the first couple are ions, is to identify the cation and anion and then put them together. So here we're naming here we have a name and we want to get the formula. So I know that my cation is copper 2+, my anion is SO4 2-. So in this case, the answer is just copper SO4. The 2+ and 2- cancel out. Barium carbonate. So barium is an alkali earth metal, so it's going to have a 2+ charge. Carbonate, you remember from the polyatomic anion chart, is a 2- charge. So again, we have barium carbonate. Nickel oxalate. So nickel is nickel 2+. That's a transition metal, and the answer is in table 2.5 in chapter 2 for the charge. So I just memorized that. And oxalate, I know from the polyatomic anion chart, is C2O4 2-. So the two charges will balance out, and we get nickel C2O4. So this is our first example of a molecular compound, disulfur dioxide. So we use the prefixes to determine the number. So di is 2. So that's going to be S2O2. So we have 2 sulfurs, 2 oxygens, S2O2. This one's a little challenging. So we have an ionic compound with some orders of hydration. So the way that we'll deal with this is how we would deal with any metal oxide. We'll figure out, because this is a transition metal, we have to figure out what the charge is on it. So I know sulfate is SO4 2-. And if we do the flip-flop method, where we flip-flop those two, I'm going to have Fe 3+, SO4 2-. So my name is going to be iron 3 sulfate. And then we have to deal with the hydrate. So I have 8 orders of hydration, so that's going to be octahydrate. Okay? So the octa stands for 8, and then the hydrate is for the 8 orders of hydration. Okay, BCl5. So this is a molecular compound, a binary molecular compound. So the first element, we just put the name of the element, phosphorus. And then we have 5 chlorine, so that's going to be pentachloride. Now this last guy, this is a challenging one. So this is one where you have to remember the the ClO4 anion. So we can have ClO-, we can have ClO2-, we can have ClO3-, ClO4-. Each one of these has a different name, going from hypochlorite, chlorite, chlorate, and then perchlorate. So because this one is perchlorate, we have perchloric acid. So we went over that one in class. So that is a bit of a challenging one, but something that you do need to know. Okay, 2 is a relatively straightforward calculation of the protons, neutrons, and electrons in an atom from the atomic symbol. So we have oxygen. I can check my periodic table, and I see that the atomic number of oxygen is 8. So immediately from that, I can assign my number of protons. Now, for the mass, we know that the mass number is going to equal protons plus neutrons. These are the ones that have mass. So in this case, my mass number is 18, and that's going to equal the number of proton, which is 8 plus n. So we get the number of neutrons has got to be 10 to get a mass number of 18. Now for the charge, charge is equivalent to protons minus electrons. So in this case, we have a charge of -2, and we have 8 protons, so if we put in minus electrons, that means that we have to have 10 electrons because we have 10 minus charges and 8 positive charges, which gives us a minus 2. Okay? So if you write this down on your exam, you would be golden. That's all you need for that one. For number 3, this is just a recast of a lot of the things we already talked about in number 1, but now I explicitly ask you for the cation and anion charge. So one of the things that makes this a little challenging is you'll notice that the anion charge and the cation charge are flipped a little bit in this case. But we wouldn't grade you incorrectly if you clearly indicated the charges, but just happened to put them in the wrong box. So for Fe3PO4, we have the following. So we know that phosphate already, so for our anion is PO4 3-. That makes life easy by remembering that the phosphate from the polyatomic anion chart is 3-. So then all we have to deduce is the charge on iron, and if we do this flip-flop method, this case the cation charge is going to be Fe2+. Okay? Silver 1 dichromate. So dichromate anion is CrO4 2-. You'll remember that from the chart. And the silver ion in this case is, I'm sorry, I put the incorrect structure here. It's the correct charge, but the incorrect structure. So dichromate is not CrO4, it's Cr2O7 2-. So even I have to remember my polyatomic ions. So I have silver dichromate, so we have the anion charge already taken care of. In this case, I made it a little explicit, so I said it was silver 1, so all you have to do is put Ag+. But you should know from table 2.5 that if we don't put silver 1, you should know that the silver has a 1+ charge. Okay, sodium hydrogen carbonate. So the anion in this case is HCO3. This will have a minus charge, and the sodium we know has a plus charge. Okay, the last one is aluminum thiosulfate. So in this case, the S2O3 will have a 2- charge. If you memorize that from the polyatomic ion chart, you would be golden. You could also deduce that from the fact that aluminum always has a 3+ charge. So that would be how you would fill out that table. Now, this is a simple one where we're doing a mole to atom calculation. So we know in this case that if we're going from moles to atoms, we're going to need to invoke Avogadro's number. So in this case, we're going to start with the 0.12 moles of barium chloride. I know that I have to finish with atoms. Okay, and that should get us the answer. So if we want to convert from moles to numbers of things, we need to invoke Avogadro's number. So we know that for every 1 mole of barium chloride, there's going to be 6.02 times 10 to the 23rd formula units of barium chloride. And in this case, it's not asking us for the number of formula units, it's asking us for the number of atoms. So what we have to do is we have to make sure that we count up all the atoms. So for every formula unit of barium chloride, there's 1, 2, 3 atoms, 1 barium and 2 chlorine. So for every 1 barium chloride, for every 1 formula unit of that, we have 3 atoms. So we can pop this into our calculators. And in this case, I will show you what I calculate. So it is going to be 0.12 times 6.02 times 10 to the 23rd times 3 atoms. And that is going to give us 2.1672 times 10 to the 23rd. So with sig figs, this is going to be 2 sig figs. So we have 2.2 times 10 to the 23rd atoms. Okay, and notice that I have a number and a unit. Alright, for the next guy, this is a pure significant figures calculation. So this gives us 4 different masses, and it asks us to calculate the total mass with the correct number of sig figs. So the only challenge to this guy is that we have masses that are on different mass scales. So we have kilograms, grams, grams, and milligrams. So you have to make sure that you get everything aligned correctly. So 940 kilograms, 0.940 kilograms is going to be 940 grams. We're going to add to that 58.2 grams. We're going to add to that 1.55 grams. And then we're going to add to that 250 milligrams, which is going to be 0.250 grams. Okay? So you could, in theory, do the unit conversions to figure each one of these out to get them all onto the same mass scale. But I just did it here in my head because I know how to do each of these. So that's the quickest way. So in your calculator, you're going to add these up. So we can add up 940 plus 58.2 plus 1.55 plus 0.250. We're going to get exactly 1,000. So let's write that in. Now the question is how do we deal with sig figs? Well, in this case, we're going to come down and we're going to decide where our least significant digit is. So in the 0.940, that's going to give us the least significant digit to the tens place. So we're going to drop that line right down there. So in this case, our answer is going to be 1,000 grams, or 1.00 times 10 to the third grams. Okay, so that makes sure that we have all of the correct significant figures in there. So in this case, we would have the maximum number of significant figures would be to the tens place. So when we write this, we have to make sure that we have 2 sig figs after the decimal point in this scientific notation. Okay? Okay, so moving on to the next sheet. We have a balancing the equation problem. So as we always do with balancing the equation problems, we want to identify the elements. So the first thing you can do is take an inventory of all of your atoms. So on the left, I have 2 aluminum, I have 3 oxygen, I have 1 hydrogen, and I have 1 chlorine. On the right, I have 1 aluminum, I have, let's see, I had oxygen there, so I have 1 oxygen. I have, how many hydrogens? 2 hydrogens, and I have 3 chlorines. So at this point, we can now go and start to try to balance. So what we know is we should try to balance things that are by themselves, meaning they appear only once on each side of the reaction. So aluminum would be a good candidate for that. So let's start by balancing the aluminum. So in this case, we'll put a 2 here. So I'll put it small in case we need to write a different one. So that's going to give me 2 aluminum, and it's going to give me 6 chlorines. So now we can go through and try to balance the chlorides, because those, again, only appear on one side. So if I have 6 chlorine over here, I'm going to need 6 of them over here. So that is going to give me 6Cl and 6H. And now we're left with the last thing we should balance, which is the hydrogen and the oxygen. So in this case, I have 2 hydrogen and 1 oxygen. And over here, I have 6 hydrogen and 3 oxygen. So the easiest thing to do is to put a 3 here. And now we're going to get 6 hydrogen and 3 oxygen. So our aluminum balances, our oxygens balance, our hydrogens balance, and our chlorines balance. So we have a correct balance of a correctly balanced formula of 1 aluminum oxide plus 6 HCl gives 2 AlCl3 and 3 H2O. Okay, so if you just follow the steps for the balancing, you'll wind up getting the right answer. You just have to go through it systematically and make sure you do it one step at a time. Okay, so for the next question, we have the density of pooled water. and they give that to us as 1.05 grams per cubic centimeter. So now what it asks for is to calculate the mass of water in kilograms required to fill a rectangular pool with dimensions of 5.52 meters by 3.75 meters by 1.2 meters. Now this problem you might think is complicated, but it's really relatively straightforward. It's just a simple density problem, but it does require some careful unit conversions. So by giving us these three dimensions for a rectangular object, we can calculate the volume. So we know that the volume will be equivalent to the multiplication of each of these. So because in any rectangular prism, the volume is equivalent to the length times the height times the width. So that's what these are. So if we take 5.52 times meters times 3.75 meters times 1.2 meters, we are going to get 5.52 times 3.75 times 1.2. We're going to get 24.84 meters cubed, because we have meters times meters times meters. And if we look in terms of sig figs, our least number of significant figures is 2. So I'm going to put a little marker here that indicates that that's the maximum number of sig figs we can get out of that. Okay, so now the next part of the question is how do we deal with calculating mass? So we have a volume. The only problem, though, is that our volume is not in the right units to work with this density. So we have to do a unit conversion. So if we do 24.84 meters cubed, and we want to convert from meters cubed to centimeters cubed, we put our unit conversions for meters and centimeters. So I know that for every 1 meter, there's 100 centimeters. And to get this so that the units match up, we have to cube it. So we have to cube that conversion. So we'll be putting into our calculator 100 cubed to get the right answer. Now that I'm in cubic centimeters, I can use my density, which is 1.05 grams per cubic centimeter. So we have to get to cubic centimeters to cancel. So we have 1.05 grams up top, and that should equal the mass of water in grams. Now the question, though, asks for the mass of water in kilograms, so my last step is to convert this to kilograms. So I know that I have to put grams in kilograms, and there are 1,000 grams for every 1 kilogram. So that's one of those things that you'll have to memorize. If this looks foreign to you, make sure you go back to the video that's in Chapter 3 on how to do unit conversions. I go over a lot of this stuff explicitly in more detail there. So this is just the setup for that. And my final answer is going to be in kilograms. So if we look at the calculator, here's how we're going to plug this in. So we have 24.84. We're going to multiply that by 100 up caret, because we're cubing it to the third, times 1.05. Okay, so we're going to get this guy. And now, so we multiplied everything on top. We're going to divide by the 1,000 on the bottom. So we get 26,082 as our answer. We have two significant figures, so you could write this as 26,000 kilograms, rounded off. Or what's always best is to write 2.6 times 10 to the 1, 2, 3, 4 times 10 to the 4th kilograms. I like this better because in this case it's a little ambiguous if you don't put a decimal point, so you would get full credit if you put that. Okay? So that is how you would solve that problem. Now, in the next one, we have a question asking us about the density of stainless steel. So it says the density of stainless steel is 8.05 grams per cubic centimeter. In industrial processes, large amounts of steel are used, and it is convenient to work with units such as kilograms and cubic meters. That makes sense because, when you're working in industry, you're not producing grams of things, you're producing kilograms, or even metric tons. So we could even convert this to metric tons, and cubic meters, which is quite a large volume of material. So what this one is asking us to do is to just do a straightforward conversion of density from one set of units to another. So this is a classic type of question to prove that you can do unit conversions, because very much like the previous question, it demonstrates that you have this handle on unit conversions, especially on unit conversions that involve calculated units like cubic centimeters and cubic meters. So in this case, we're going to start with our 8.05 grams per centimeters cubed. We have to have our answer in kilograms per meter cubed. So that's where we know where we're going. So the way that I would start would be to just get the grams to kilograms correctly. So we know that for every 1,000 grams, there is 1 kilogram. So that allows grams to cancel out. Now we have to deal with the centimeters cubed. So again, this is a calculated unit. So we can write our centimeters and meters conversion. So this will cancel centimeters down the line. So we know that there's 100 centimeters for every 1 meter. And since we're dealing with cubed units, we have to cube this conversion. So in just 2 simple steps now, we've been able to convert grams to kilograms and centimeters cubed to meters cubed. Okay, so when we plug this into our calculator, I am going to take 8.05 times 100 cubed and then divide this by 1,000. And you're going to see that you get 8,050 kilograms per meter cubed. Now, with sig figs, though, we're not going to just leave this as 8,050. We have to make sure that we get the correct number of sig figs. So we started out here with 3 sig figs. So my preference would be to say that this is going to be equivalent to 8.05 times 10 to the third kilograms per meter cubed. Okay? So that's how you would do a unit conversion like that. Now make sure again that you get the sig figs correct. That's a gimme. Those are gimme points on these. Okay, so question number 9 is getting into the concept of the mole. So this is a question where we ask you to do some conversions through the mole, basically some mass to mole conversions, and then some mole to mass and mole to numbers of formula units and ions type calculations. So in this case, it asks how many moles of barium phosphate are in 2.64 grams of this compound. So we know that we have to, in this case, we're doing a mass to mole calculation. So we're going to need the molecular weight. So to calculate that, we can grab the molecular weights of barium and the other compounds. So to show you how I'm going to do this, I'm going to look up the mass of barium, and I get 137.328. We have 3 of those, so we're going to take that times 3. Then we're going to add to that phosphate. So phosphate, I have 2 phosphates, and the molecular weight of phosphate is 30.97. So we have 2 of those. And then we have to do oxygen. So there are 8 oxygens. 2 times 4 is 8. So 8 times 16. So I get a grand total of 601.92 grams per mole. Now in the exam, generally speaking, you can round these to 2. The instructions will generally tell you what to do, but pretty much all of my instructions always say to round to 2 decimal points, so that should get you the right answer. So once we have the molecular weight calculated, based on the number of elements present, we can simply do our conversion. So 2.64 grams of barium phosphate. And we know that for every 1 mole, there is 601.92 grams. So this will tell us how many moles we have, because grams will cancel. So 2.64 divided by 601.92 is going to give us 4.39. Remember, this is 4.39. I have 3 sig figs in my number here. So 4.39, so I'm rounding, and we're going to count over. 1, 2, 3, so 4.39 times 10 to the minus third moles of barium phosphate. Okay. Now it asks us to calculate how many formula units are present in 2.64 grams of barium phosphate. So to calculate formula units, now we're calculating quantities of things. So in this case, we're going from mass to moles, and then from moles to the number of formula units. So since we calculated the number of moles, we can skip this step because we just did that. So I can just grab my number of moles, so 4.39 times 10 to the minus third moles of barium phosphate. And then we can convert from moles to the number of formula units. So here this is going to be 6.02 times 10 to the 23rd is our relationship formula units per mole. So for every 1 mole, we have 6.02 times 10 to the 23rd formula units. So that is going to be equivalent to 4.39. So if we plug this into our calculator, so 4.39 times 10 to the minus third times 6.02 times 10 to the 23rd, I get 2.64 with the correct number of sig figs times 10 to the 21st formula units. Okay, so that would be my answer. Now the last one is asking us about the number of ions present in 2.64 grams of barium phosphate. So in this case, we have to count up how many ions we have. So how many cations we have is 3. So we have 3 barium 3 plus. And we have 2 anions, 2 PO4, 2 minus. So that's going to give us a total of 5 ions. So if we take 2.64 times 10 to the minus times 10 to the 21st formula units of barium phosphate, we can then multiply by the fact that there are 5 ions per formula unit. So for every 1 formula unit, we have 5 ions, and that is going to give us 1.32 times 10 to the 22nd ions. Okay. Oops. There you go. 1.32 times 10 to the 22nd ions. Again, making sure that you have the correct number of sig figs. All right. So the next problem is an empirical formula problem, and these are very, very common on the first exam because they demonstrate a number of principles that you need to use. So in this question, it says a sample contains only carbon, hydrogen, and nitrogen. So already there's something a little different. So far you've only seen carbon, hydrogen, and oxygen, but you'll actually find out that there's really no difference whatsoever because the process for determining it is exactly the same. You just, instead of using oxygen, you use nitrogen, and you'll get the exact right answer. So in this case, it gives us the percent of carbon and the percent of hydrogen. So we can automatically figure out, since everything has to add up to 100%, what our percentage of nitrogen is. So in this case, we're just going to take 100 minus 58.5 minus 7.36. So our percent is going to be 34.14, keeping in mind that we have one significant figure there, percent of nitrogen. So that's one thing that you can do right off the bat to make your life a little easier, is just to calculate the percent nitrogen knowing that these have to add up to 100. So since we have percents, we're going to assume that we have a 100-gram sample. So that means that we're going to have 58.5 grams of carbon in a 100-gram sample, 7.36 grams of hydrogen, and 34.14 grams of nitrogen. And we have to calculate the number of moles of each of these. That's the first step. So in this case, this will be 12.01 grams for every 1 mole. So we invoke the atomic weight of carbon to get the number of moles. So in this case, 58.5 divided by 12.01 is going to equal 4.87 moles of carbon. We use the molecular weight to convert to moles of hydrogen. So this is going to be 1.008 grams for every 1 mole. So 7.36 divided by 1.008 is going to give us 7.30 moles of hydrogen. And lastly, we have 34.14 grams of nitrogen, so this is going to be 14.0 grams of nitrogen for every 1 mole. You can be a little bit more exact if you want. That is, yeah, it's pretty close to 14. If you want to include some extra decimal points there, you can, but this will give you the right answer. So if we take 34.14 divided by 14, that is going to give us 2.44 moles of nitrogen. You can see that right there. So now what we're going to do is we're going to take the ratio of each of these. So we're going to, using the smallest number of moles, which is the moles of nitrogen, we're going to divide each one by the smallest number of moles. And we're going to figure out what the ratios are. So for the first one, that looks like it's going to be about 2. I'll give you the exact number. That's going to equal 1.995. So that's going to be about 2. We can assume that this is 2. 7.3 divided by 2.44, that's going to be 2.992. So this is close enough that we can say that that's going to be 3. And then down below, this is going to be equal to exactly 1. So our empirical formula based on this is going to be C2H3 and 1. And now for the second part of the problem, it asks us to determine the molecular formula based on the molecular mass of 82.1 grams per mole. So in this case, we can come up with the empirical formula weight. So that's going to be 12.01 times 2, because there's 2 of them. 3 plus 3 times 1.008 plus 1 times 14. So that's going to give us a molecular weight of 41, an empirical formula weight of 41.0 grams per mole. So we can come up with the ratio now, which is going to be 2. So 82.10 grams per mole for the molecular formula divided by 41.0 grams per mole. That's going to give us an exact ratio of about 2. So we know that we have to take our empirical formula and multiply it by 2. So the correct answer here is going to be C4H6N2. Okay? So that's how you would deal with that. For question number 11, we're switching gears now and going into the topic of isotopes. So for question 11, the question says, bromine has an average atomic mass of 79.909 AMUs. Then they give us some information about one of the 2 isotopes. So they say there's 2 isotopes. Bromine 79 has an exact mass of 78.918 AMUs and has an atomic abundance of 50.4%. So then they want to know what is the exact mass of the other isotope. So it is our job to calculate the mass of the other isotope. So the equation that we refer back to from class is for any isotopic question is that the fractional abundance of a given isotope, so the fractional abundance of Br79 times its exact mass, will tell us how this contributes to the overall average. So we can write one of these terms for each of the two different isotopes. So we have the fractional abundance for bromine 79, we have its mass, and then we can put the fractional abundance for our bromine question mark times its mass that we want to solve for. And this has got to equal the average mass, which is 79.909 AMUs. So we can plug in with some information from the question. So here our fractional abundance is 0.504, or 50.4%. The mass in this case is going to be 78.918 AMUs. That's what the problem tells us. Since there's only two isotopes, the percent abundance has got to add up to 100. So here I have 0.496. 100 minus 50.4 is going to equal 49.6. And then we're solving for the mass of the unknown isotope. So now we've sort of brought this problem down into a little bit more of a manageable form. So when we're doing sig figs, we're going to want to make sure that we take this one step at a time. So the way to do that is, let's do our multiplication first. So if we take 0.504 and multiply that by 78.918, we get 39.775 AMUs. With sig figs, the best we can do is 3 from this guy. So I'm going to mark this one with a 3 significant figure designator right there. And then we have our 0.496 times the mass of the question mark is going to equal 79.909 AMUs. So now we can do our subtraction. So we're going to take 39.775 AMUs minus 39.775 AMUs. So when we do our subtraction here, we're going to make sure that we get the correct number of significant figures. So 79.909 minus 39.775 is going to be 40.134. So here's my significant figures. And that's going to equal 0.496 times the mass that we want to know. So if we divide this by 0.496, our mass is going to be 80.91 AMUs. And since we have 3 significant figures and 3 significant figures, we're going to get 3 significant figures. Okay, so in this case we have one isotope with a mass of 78.918 AMUs. That represents 50.4% of the sample, and one with a mass of 80.91 AMUs. That represents 49.6% of the sample. So that's how you would solve one of these guys. Our last question is a limiting reagent problem involving stoichiometry. So in this case, solutions of sodium hypochlorite can be prepared by the following reaction. So it gives us a balanced chemical equation. And then it says in a given reaction, oops, zoom that out a little bit. In a given reaction, 32.0 grams of NaOH, molar mass is equal to 40.0 grams per mole, so they help us out with molecular mass, are reacted with 1.75 grams of Cl2. They give us a molar mass there. And now they ask us to determine the limiting reagent. So in this problem, the way that I always approach it is they give us 2 different amounts of 2 different reactants. So I come up with the theoretical yield that each of these would give us. And then the limiting reagent will give us the one that has the lower theoretical yield. So that'll be the one that limits the reaction. So we'll start with the 32.0 grams of NaOH. So we need to get this to moles so that we can come up with the stoichiometry. So we'll plug in the fact that there's 40.0 grams for every 1 mole. Now that we're in moles of NaOH, we can convert this to moles of product. So you can choose any product, but if you want to make your life easier, if you look a little bit ahead, it asks for the theoretical yield of NaClO. So let's go ahead and use NaClO as our test case to see how much it produces. So for every 1 mole of NaOH, for every 2 moles of NaOH, we produce 1 mole of NaClO. Okay, so what this is doing is this is allowing us to go from apples to oranges, so we can make sure that we have the correct number of moles of product. And since we're looking for a theoretical yield, we can then convert NaClO into a mass, and we can use the molecular mass, which is provided down below. So for every 1 mole of NaClO, we have 74.4 grams. Okay, so you can plug this into your calculator and get 32 times 74.4, and then divide by 40, and then divide by 2. So for this guy, I get 29.76. Remember, with sig figs, we have 3 sig figs in the answer, so I get 29.76 grams. And just to show you the calculator, what I did was I took 32 times 74.4, which was what was on top, and then I hit the divide button for the 40, and then I hit the divide button for the 2, and that's what gets me the right answer. Okay, so now we can go ahead and calculate what the theoretical yield would be for our mass of Cl2. So in this case, they give us 1.75 grams of Cl2. The molar mass in this case was 70.9 grams for every 1 mole of Cl2. We have 1 mole of Cl2 for every 1 mole of NaClO. And then again, we convert moles of NaClO to mass. And for this, I get 1.84. Well, with sig figs, let's not round. 1.836 grams, and then with sig figs, I'm going to have 3. So the final answer here would be 1.84 grams. The nice part about this is you've already calculated for the second question, so it says calculate the theoretical yield. So in this case, you can just bring this guy down as your answer and write 1.836 grams, which is going to equal 1.84 grams of NaClO. This is one of those instances where you've already done the work, so you don't have to show the work all over again. Just indicate with an arrow that you're calculating that. Okay, and in the last part of this question, it says calculate the percent yield of NaClO. So, and then it says if 1.75 grams are actually formed during the reaction. So in this case, we know that percent yield is equivalent to the actual yield divided by the theoretical yield times 100. So if we plug in, that's going to be 1.75 grams, which is what they tell us is the actual. 1.84 grams is the theoretical. That's what we calculated. We multiply this by 100. So our percent yield will be 1.75 divided by 1.84 times 100. So we get a percent yield of 95.11%. And with sig figs, since we have 3 sig figs, the final answer is going to be 95.1%. Okay, so that basically takes you through the practice questions. We'll have an opportunity to go over these a little bit in office hours before the exam if you have any questions, but this kind of gives you a full explanation of everything. So I hope this is helpful, and good luck with your first exam.